Hi, my name is Ben. In this paper, we introduce a new representation of HD maps for motion forecasting in self-driving. In order for self-driving cars to plan a safe route, we not only need to detect surrounding actors, but also predict their future behaviors. This is called motion forecasting. The task is challenging by making predictions for the past trajectories alone, as future prediction contains much uncertainty and involves complex interactions. High-definition maps, however, provide useful clues for motion forecasting, as in most of the time, traffic agents behave as following the map topology. Also, interactions between agents largely depend on the semantics and geometry of the map. One can capture these map wires by hand-designed rules. In the case of vehicles, we can first solve the vehicle lane association problem, and then get possible future trajectories by assuming that the vehicle will continue to follow the lane. However, the performance of the heuristic-based approaches is not good enough, as they cannot handle complex behaviors very well. An alternative is to jointly learn the map representation together with the actor trajectory. Towards this direction, previous methods mostly use raster image representation to encode past trajectories in HD maps together, and use 2D convolution to process them. Both data modalities are rendered in the same bird's eye view space to preserve the spatial information, while semantics are encoded with different colors. However, this brings information loss during rasterization. Also, 2D convolution is not efficient in processing graph structured data. Instead, in this paper, we propose a novel approach that extracts actor and map features separately with specialized neural networks, which introduces minimal information loss. A 1D ConvNet is used to encode actor trajectories, and a graph ConvNet is applied to graph structured map data. Both actor features and lane features are then fused together to predict multimodal future trajectories. Here we explain how we convert the raw map data to a lane graph while preserving the geometric and semantic information. The raw map data is composed of a set of directed polylines representing the lane center lines. In our equivalent lane graph, we define the graph nodes as the small line segments that compose the polylines. This representation not only preserves the detailed shape of the lanes, but also enables fine-grained lane actor interactions. While the nodes capture the geometry of each lane, we use the edges to preserve the semantics between lanes. In particular, we inherit the same 4 types of semantic connectivity that exist in raw map. Take the red node as an example. It has predecessors indicating where the traffic comes from, and successors showing where the traffic goes to. It also has left neighbor that defines the parallel lane at the left side, and the right neighbor that defines the parallel lane at the right. These multi-type and sparse edges enable structured information propagation within the lane graph. Given the nodes and edges defined in the lane graph, we apply graph convolution to extract features on the nodes, where the receptive field follows the topology defined by the edges. Specifically, we initialize the node feature as a combination of the displacement of the segment vertices and the position of the segment center. We then define one step of node feature update using the proposed multi-scale lane convolution. Lane convolution consists of 3 parts of features. The first part is the self-node feature update, where X denotes the node feature matrix and W denotes the convolution weights. The second part is neighboring feature aggregation, where AI denotes the adjacency matrix for each connectivity type. This part helps the node to see left and right lanes to understand the lane change behavior. The third part is predecessor and successor feature aggregation. We make it multi-scale as we need to plan for a long future horizon for vehicles along the lane. Given the proposed multi-scale lane convolution operator, we build a graph ConvNet called LaneGCN and apply it on the lane graph to extract node features. The architecture is simply a stack of 4 multi-scale lane convolution blocks. After the LaneGCN, each node in the lane graph gets updated with information from nearby lanes following the map topology, and is therefore useful for motion forecasting. Given actor features denoted as rectangles and the lane features denoted as circles, we propose to model the four-way interactions between them. We first propagate information from actors to nearby lanes, which is supposed to provide real-time traffic information for the lane features. For example, whether a lane is occupied by traffic or not. We then propagate features along the lane graph so that traffic information can be broadcasted to faraway regions efficiently. After lane graph propagation, we fuse the updated lane features back to the nearby actors so that each actor receives most up-to-date map information. Lastly, we model interactions between actors to produce more socially compliant trajectories. In practice, lane-to-lane module is implemented by LaneGCN, while the other three modules are implemented by a spatial attention layer. After four-way interactions, each actor receives contextual information from nearby lanes and actors. Therefore, we are able to produce multimodal trajectories. In particular, the prediction header outputs a fixed number of K trajectories for each actor, as well as a confidence score for each trajectory. We evaluate our approach on the Argoverse benchmark and compare it with the top-ranked methods in the first Argoverse motion forecasting competition. We show significant improvements over the state-of-the-art in terms of average and final displacement error and miss rate. Specifically, we show around 9% relative reduction in FDE over the second-best method in the settings of single model output and multi-model output. Here we show ablation study on different modules of our model. Our baseline is an actor-only model without using mapped input, and we show that exploiting interactions between actors helps motion forecasting. We then introduce map data to our model with the proposed LaneGCN for lane feature extraction. Lane feature and actor feature are fused together for prediction. We show that adding maps significantly reduces the prediction error, and the gain is even larger than that from multi-agent interaction, indicating that map provides crucial information for accurate future prediction. Lastly, our proposed four-way interaction further improves the performance. Here we show ablation study on the proposed multi-scale lane convolution. The vanilla graph convolution updates the node feature by aggregating information from its connected neighbors. In the second line, we show that adding the self-node update makes learning easier with better performance. Adding multi-type edges with separate weights helps by encoding the semantics of lanes explicitly. Lastly, adding dilated convolution along the lane effectively enlarges the actor's receptive field in a structured way, and therefore leads to further performance boost. Here we show qualitative comparison with top three methods on several challenging scenarios. In this right-hand scenario, our model is the only one that captures all possible modes, showing that by better understanding the map, we can produce more diverse trajectories. In this weight to turn left scenario, since the past trajectory provides limited information, map plays a more significant role in prediction. Our model is able to produce more realistic trajectories, while other methods produce divergent trajectories. In this deceleration scenario, while all models fail to capture the correct trajectory, our model predicts the trajectories that better follow the lane curvature. In the last example, where the actor accelerates to pass the intersection, all four methods fail to capture this behavior. Here we show a demo video of our approach on Argoverse. Green circle denotes the predicted trajectory of our model. Red circle denotes the ground truth trajectory of the same actor. Blue circles denote the trajectories of the surrounding actors. From the video, we can see that our model is able to predict very accurate trajectories in different map topologies and traffic scenarios. To summarize, in this paper, we propose a new representation for HD maps, which is the lane graph. The nodes and edges of the graph preserve the map geometry and semantics with minimal information loss. We also propose a new operator for feature extraction on the lane graph, namely multi-scale lane convolution, which performs feature aggregation efficiently following the map topology. To better exploit the map information for our end task, motion forecasting, we propose four-way interactions between lanes and actors. Lastly, we set the new state-of-the-art results on the Argoverse benchmark. Thank you.